What's up, guys? In this video we're going to be talking about infinite limits. So I'm going to introduce what they are, give you the definition, and then go ahead and show you some properties of these infinite limits. And the idea behind an infinite limit is, if you'll recall, our original limit, we had x going to c of f of x is equal to L, and this L value is some real number right here. 1, 2, 3, pi, whatever that number is, it was some real number. Now we're going to be taking a look at limits where x is going to c of f of x, and that limit is equal to infinity. So what might that look like? Well, on a graph, it might look like something like this. And I'm sure you guys talked about vertical asymptotes at some point in algebra, so maybe we have a vertical asymptote right here on our function f of x, and maybe our function looks something like this. So our limit, if this is c, right here, this is c, as x is approaching c, our f of x values, as you can see, are getting closer and closer to what? Well, they're getting closer and closer to infinity, but we don't really say that. We say they're increasing really without bound. So they're continuing to increase the closer you get to c. And that's kind of what this definition is going to be based on. And similarly, if we were to say the limit as x goes to c of f of x is equal to negative infinity, we'd expect them to be decreasing without bound. So maybe there was another asymptote over here on this graph, and instead of looking like this, the function did something like that. And then you can see as x is getting closer and closer to c, we're decreasing without bound. But what if this side of the graph maybe looked like this? Then on one side we're increasing without bound, and on the other side we're decreasing, so we're going to have to reintroduce those one-sided limits. So as we're coming in from the left here, we would say the limit as x is approaching, let's call this point a from the left is going to be infinity, but as it's approaching, or sorry, this is from the right, but as it's approaching a from the left, it's going to be negative infinity. So we're going to talk about all that and go ahead and try and define it. So we're going to go ahead and look at the definition of an infinite limit. And it is defined as, let f of x be defined on some open interval containing c, except possibly at c. Very similar to that epsilon delta definition. The limit as x approaches c of f of x is equal to infinity, so this is our positive infinity. If given any, is that if we're given any m greater than 0, so essentially for any capital M value greater than 0, and that is an arbitrary number, just like epsilon, we can find a delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then f of x will be greater than m. Now, what does that tell us? Well, what it lets us know is that if we get closer and closer to delta, we will get Alright, so let's take a look at the definition of an infinite limit. Let f of x be defined on some open interval containing c, except possibly at c itself. So that's very similar to our epsilon delta definition. The limit as x approaches c of f of x is equal to infinity means that, so essentially that means that if we are given any m greater than 0, capital M greater than 0, that's just like epsilon, it's an arbitrary value that we are given. We can find a corresponding delta greater than 0, such that if 0 is less than the absolute value of x minus c is less than delta, then f of x will be greater than m. Now, why does this work as a definition for the limit? Well, based on this limit, what we know is that as x gets closer and closer to c, f of x is continuing to get bigger. It's continuing to approach infinity, and it's growing without bound. So if we were to pick some arbitrary m value, regardless of how big that m value might be, if we were to get our x values close enough to c, we would be able to find that all the x values inside that interval right around c would still yield f of x values that exceed that m value. And why is that? Well, let's look at a sample graph. Let's make this my y-axis and my x-axis. I'm going to have a little vertical asymptote right here with c, and the graph's going to look something like this. So as you can see from our interpretation, it does look like the limit as x is approaching c is going to be infinity. And how can we show that? Well, for whatever m we get, that m could be as high as here, or even higher. We can make it as high as we want. We will be able to find a delta such that this is c minus delta and c plus delta, such that all the f of x values that we get from x values inside this interval, except at c, will give back f of x values that are greater than m. And why can we do that every single time? Because as m gets bigger, because as x gets closer and closer to c, f of x gets infinitely bigger, we just need to get close enough to c to find an interval that gives back f of x values that are going to be bigger than m. So that is our definition of a limit as x approaches c of f of x when it's equal to positive infinity. It's really easy to define what happens when we're looking at the limit approaching negative infinity. All we have to do right here is change this sign to a less than sign, and then correspondingly all we have to do is change this sign right here to a less than sign. So we can make m as low as we want. We can make it essentially as negative as we want, approaching negative infinity. And as long as we limit our x values in that tiny interval, we will always be able to find f of x values in that interval that are lower than m. Why? Because as x is getting closer to c, f of x is getting closer and closer to negative infinity. Not really closer, because you can't get close to infinity, but it's decreasing without bound, and it's continuing to decrease. And it appears as if it's going to go all the way down to negative infinity. So that's how you define that overall limit. Well, let's look at this let's go back to our positive limit, and what if we want to look at the limit only from the right side? Well, we've done this before. We have to change this because we have our positive limit again. So here's our positive limit. All we have to do is get rid of these absolute values right here. Why? Because now we're selecting x values on this number line that are from c to c plus delta. So we're only looking at x values here, which are x values that are coming in towards c from c plus delta to c. They're coming in towards c from the right side. Similarly, if we wanted to look at this limit from the left, and this should all be familiar from that epsilon delta stuff we did before, we're going to change this to c minus x, and that means we're going to start looking at x values that come from, this should be c, and that come from c minus delta, so we're looking at values here. So as we pick different delta values, we're looking at x values that are getting closer to c from the left side. And similarly, if we wanted to look at this for a negative infinity, all we have to do is correspondingly change our inequalities right here. And then if we wanted to do negative infinity from the positive sign, all we do is we bring this back to an x minus c. And that's all stuff that should kind of make sense if you understood that epsilon delta definition. So that's how we're going to go about defining these infinite limits. Next, we're going to look at some of the properties of infinite limits. So when we take a look at these properties, they're going to seem pretty intuitive, and we are going to do them without proof for now. So in this video, we're not going to be proving these, although I assure you, you definitely can. So these are properties of infinite limits. And what we have for these properties right here, we're going to let the limit as x goes to c of f of x equal infinity. We're going to let the limit as x goes to c of g of x be negative infinity. And we're going to let the limit as x goes to c of h of x be L. And let's look at some of the properties we get. So we're going to say that the limit as x approaches c of k times f of x is going to be infinity, given that k is greater than 0, and it will be negative infinity, given that k is less than 0. That should make some kind of sense. We're going to look at the limit as x goes to c of k times g of x, and of course this will be negative infinity if k is greater than 0, and infinity if k is less than 0. Now we're going to take a look at some of the multiplication properties. or I'm sorry, addition. Actually, let's take a look at addition. If we have f of x plus h of x, the limit, we get infinity. And if we have f of x minus g of x, we get infinity. If we have f of x, and let's write this, instead of just plus h of x, this is actually plus or minus h of x. So it doesn't matter if we add or subtract, we're still going to get infinity. Now here, it does matter that we're subtracting g of x. If we add g of x, we're not really sure what that limit is going to be. So, and now we can do the same with g of x, plus or minus h of x is going to give us back negative infinity, and g of x minus f of x is going to give us back negative infinity. Okay, now let's take a look at some of the product properties we're going to get. So the limit as x goes to c of f of x times g of x is going to be negative infinity. The limit of f of x times f of x, or some other function where that's approaching infinity, is going to be infinity. And g of x times g of x is going to be infinity. And then the limit as x goes to c of h of x times f of x is infinity. And this is granted that L is greater than 0 right here. And this is going to be h of x times g of x is going to be negative infinity. And this is granted that L is going to be greater than 0 as well. And if L was less than 0, you would end up flipping those signs. And these should all seem pretty intuitive. When you add infinity to a real number, you're going to get back infinity. When you multiply infinity and negative infinity, it's going to be negative infinity because you have that negative out front. So there's another set of properties that have to do with that quotient rule that are also pretty intuitive. If I have something like f of x over h of x, this will be infinity, provided that L is greater than 0. If L is less than 0, it will be negative infinity. And similarly, g of x over h of x will be negative infinity, provided that L is greater than 0. Now, these are the important ones right here, and they're still pretty obvious. This is going to be 0, h of x over f of x. If you have some number over another number that has infinite magnitude, you're going to get 0. And similarly here, h of x over g of x will also be 0. So these are some important properties of our infinite limits, and you can go through and show all of them. It is very tedious, but it is something you can do with those definitions. And yeah, so that's everything you need to know at this point about infinite limits.